Alright, hey, I'm Brent Mallory, this is Alex Ray, Matt Forrest, and we have the kinematic extravaganza for Battle Frog Rube Goldberg device. Thank you for having us here today.
So to get us started, we want to talk a little bit about our project scheduling and first show you an updated version of our Gantt chart since the last time we've spoken. And so to give a brief overview, we are very close, or closing in on the end of the project. This screen capture was taken on October 23rd, and this vertical line right here represents the due date of the DP2 report, which we are now past. And so we are scaling in on the last three tasks, including the industrial design, designing for manufacturing, and the presentation of the final results. So what that Gantt chart doesn't show, and what we feel is important to the team to know, is the relationships between the tasks and how they interact throughout the design process. And so to help illustrate these a little bit better, we decided to go ahead and make a design structure matrix, as seen here, with the key to the left. And each of these X's represents a task dependency, and so we read it from the horizontal and also the vertical, and where the X meets the two tasks shows the relationship. So for example, what our Gantt chart doesn't show us is these two X's down here, the relationships between task I and B being the product architecture and identification of customer needs, and also tasks K and C being the designing for manufacturing and the economic analysis. Both of these tasks or all four of those tasks are very integral to the project, and the interrelationship of both is not shown by the Gantt chart, but does help the team to know this as we move throughout the project.
So for our project, we decided to look at patents and property that had previously been applied for by other companies and businesses, so that we didn't run into any problems kind of using somebody else's idea. This is just a sample of our table. We found about 5 projects that kind of involve the same concept of what we want to do. So this, for example, was a jigsaw puzzle, and though it's a very simple concept, they used theorems, formulas, and equations from physics lecture for young students, and had them put them together into an educational jigsaw puzzle so they could figure out what goes where and what the kind of foundations of these physics equations are. So we thought this was a fabulous idea, and we are going to be using the formulas and theorems that they used in our project. However, we wanted to spice it up a little bit, and so we are going to be using obstacles and challenges and kind of gear it more towards upper class high school students to kind of entertain them while teaching them these concepts that this jigsaw puzzle was attempting to teach the younger students.
So an important part of this project is to do the overall black box diagram to show the main inputs and outputs of the Rube Goldberg device that we're trying to make, to pinpoint some of the functions that we need to add to it. So the 3 main inputs are going to be the Arduino code input by the user, the upper class student, the ping pong ball obviously, and that ping pong ball carries its own potential and kinetic energy into the Rube Goldberg device. And the outputs that we're going to have of the code input, this leads directly to the Arduino track selector. So in our machine, the envisionment is to have a single track that then branches off into 2 with a selection track selector in the middle, controlled by the Arduino electric motor, and thus the code input of the user. Secondly, our output is also going to be the ping pong ball. It's going to be fully functional when it exits the machine, with no cuts, scratches, or dings. And most importantly, we're going to have an educational value expelled from this device and hopefully absorbed by the user, which is the main reason that we got together to make this machine. And so to break down the black box a little bit more, our inputs and output don't really change. but it does help cycle these into one output together. So our Arduino code input, as we said, is going to take user input and operate an electric motor, which then helps facilitate the successful passing of the ball throughout the machine. The ping pong ball is going to be accepted into the trap, travel throughout the obstacles, and be expelled by the machine. And the kinetic energy and potential energy of the ball as it enters the machine is going to then be converted to and from potential energy throughout the machine, depending on the trajectory and where the track is located. And our idea is to have the students solve for potential energy and kinetic energy at certain points, and then make observations as they use the machine to determine whether they are using it correctly or not.
So for this project, we generated a concept combination table and put them together. So over on the left side over here, we have the concept combination table, and we divided our project into 3 subfunctions. These 3 subfunctions were the conservation of energy, the kinematics of projectiles, and momentum. So within each subfunction, we had 3 obstacles that related to these theorems of physics, and we combined them in different ways that we thought would work best together to teach students what they were going to be doing during the project. Over here we have our 5 solutions that we came up with, drawn out, and so we decided to go with number 5, which included the drop from varying heights, the track switch, the loop, and the jump, and yeah.
And so we also took these concepts that we saw on the last slide and created a reference and scored them against each other qualitatively, and then translate that into a quantitative reading to help us determine which concepts we wanted to move forward in development with. And so to choose a reference concept, we tried to choose the one that was the most simple. And so to us, that was the jump, and each of the other concepts that we chose, being the loop-the-loop, ball drop, elastic collision, weighted ball drop, track switch via Arduino, and the disconnected track, were all scored in relation to this. So they were scored in 6 categories: the ease of assembly, ease of use, durability, functionality, educational value, and portability, and we assigned relative weights to each of these categories based on how important we thought they were to the success of the machine. And then each of these categories of each concept was then given a score in reference to that category of the reference concept, being the jump. So a 1 signifies a much worse than the reference rating, a 2 signifies worse than, 3 is same as, 4 is better than, 5 is much better than. And then each of these ratings was then multiplied by the ease, or the category's weighting for the corresponding rating, and then these weighted scores were then added up to create a total weighted score to help us decide which concepts to move forward with. And so at the end of the analysis, we decided to move forward with the development of the loop-the-loop, ball drop, reference concept being the jump, and also the Arduino track selector.
So once we figured out what we wanted to continue on building, we decided to send out a survey to the population, friends, family, teachers, students. We sent it out over social media so we could get a fair amount of responses. And our survey results, this is just a short summary of what we got. We asked them about the teaching technique that they received in class, which mainly included lectures and demonstrations. And we asked whether they enjoyed the teaching techniques received. Most of the students said somewhat, and the teachers said they did enjoy what they did. The students were going through 2 to 3 physics classes a week, and the teachers were about 2 times a day, teaching a class about 2 times a day. Both of them showed interest in our project. And over here, we have a summarized table over what these interests were. No one was either not interested or extremely interested in our project. However, we had a couple people that were somewhat interested. The majority of our survey responses were interested in our project, and there were a couple that were very interested in our project. So this showed us a lot of promise in the project that we're creating.
Okay, so to better figure out what kind of challenges our Rube Goldberg device would face, we came up with a FMEA, or failure modes in effect analysis, to figure out which failure mode would be both most likely, most dangerous, and could be what we need to address in our design. And through that, we found that rough track and a unlevel track would be the highest RPNs, so they would be most likely to occur while causing significant enough damage to make our product either unusable or difficult to use by the customer. We also found some very high danger failures, but they were extremely unlikely and most likely would occur from improper use of the product, so we decided that they were not needed to be dealt with at the current time. For our economic analysis, we went through a repayment plan to figure out if we could both have VTEPs pay a lump sum up front, and then so we could go through our design, and then 3 or 6 quarters later be able to repay over 6 quarters that sum. And the lump sum that we were asking for is $76,000. At quarter 7 through quarter 12, we'd be paying a annuity of $6,751.85, and that would be at a nominal interest of 12% per year. Some important equations we went through in this analysis was to get the effective interest rate. We used the equation that was provided for us in the class, and through that, for over the 12 quarter period, we get a yearly effective interest rate of 12.68%. And in order to find what our annuity would be over the repayment period, we first found a P prime, which from that $76,000 and over 6 quarters of gaining interest ended up being $90,747.97. And then from that P prime, we plug that into the annuity equation to get our final value of $16,751.85 that we pay back to VTEMPs over those 6 quarters. And in conclusion, we went over past inventions and property that we could find that was similar to make sure that our device was different enough that it wouldn't infringe on anyone else's intellectual ideas. We generated and tested key concepts such as the loop, ball drop, the Arduino switch, to see if they were actually feasible to make and for the ball to go through. And for our investment analysis, we went through a repayment plan to make sure that both VTEPs could be able to pay us the money and upfront, and then we would be able to repay them while also making a profit with our BRG. If you have any questions, our emails are listed. Please contact us if need be. And these are our image sources for any outside images we used. Thank you.